So let's look at implementing this, right? That'll maybe be the second to last thing we do here. Let's go back. When it comes to actually implementing this in a program, so you can do this in ease. I have that example. What I want to show you is how to do this in Python again. So this example is, what do I do? So just to start off, let's start here. So I'm specifying my problem geometry. I have my temperature boundary condition. I'm going to express the coordinates in terms of a normalized length. So x and y are in terms of x bar and y bar, which is just the position 0 to w or 0 to h. So what we want to do in this problem is we're trying to solve for the lambdas first. We need to create a space for these unknown constants. So I'm taking my solution that we just developed, which is here. So I'm going to say for every I in range n, I'm going to, and keeping in mind in Python, I starts at 0. I'm going to compute the value of lambda, right? This comes straight from my eigencondition, that solution. It's the same thing. This is the thing we just very laboriously solved for. So it's any constant for any individual index I is this stuff here. And I think, keep in mind that we're starting here at I equals 0, so you may need to change the values of I or whatever. But we're solving explicitly for the constants here. So once you have the lambdas and you have the constants, then it's a matter of going through and computing any individual t sub I, which I've called t lambda, or t lambda. So I allocate the space. Again, I iterate over all this range n and compute the value. This is the function that we just wrote out like 6 times, right? It's just the constant, cosh, sinh. And then in the end, what we do is add up the individual values that we compute here. One question is this n. Isn't that infinity? Well, like I said, no. You have to do something. So let's pick n is equal to some number. I just said 21 as a place to start. So, OK, we did this. Now what I'm doing is I'm taking this whole thing, putting it in a function where I pass to that function my x and y coordinate. And then down here, I'm going to create a mesh of positions in x and y. So I've got, 1,000 positions in x. What, 5 positions in y? Oh, no, this is something. This is, 5 positions. This is one plot. Then we'll do another plot later. So doing 1,000 positions in x, I want to look at 5 slices in the vertical y, and then plot those out and see what it looks like. So let's do that part first. Just see if I can run this. OK. So first of all, pretend you don't see the top line. Just ignore that. What we're looking at here is my temperature. Again, 0 is my boundary condition. So it's matching the boundary condition here. dt dx is 0 at x equals w. So that's matched. And I'm seeing what is a function of y. So blue is at 0. So it's the very bottom. And then 0.25, 0.5, 0.75. Right? So that all looks really good. It kind of is intuitive to what you'd expect. The weird thing and the thing that catches your eye is this one, right? So what's going on there? Well, we have, as I said, modeled this as a summation of sines and cosines. At that boundary, at that one corner, we have a temperature that is on one side held at 0, and on the top side is held at TH, whatever it is. So you have this discontinuity, this single point that's trying to be both 0 and TH at the same time. So in order to fit that, it's doing some really weird stuff with the sines and cosines coefficients at that position. In all these positions, it's just fine, but here it's not so great. So what you could do to address this is, 1, have more realistic boundary conditions. 2, add terms to this. We only use 21 terms, but maybe if we added terms to our function, sorry, stop myself. This is what the surface plot looks like. And you can see the same thing. So again, you see this nice this nice behavior, a really nice model, really simple model, analytical, and it's behaving really well pretty much everywhere except for right up in the corner and on this top boundary. So if you don't care about what's happening at that boundary, you probably don't need to go any further than this. But if you do, then we need to maybe go back. So let's close this. And let's go back and maybe increase the number of terms here. So instead of 21, let's just make this 200. So you'll notice, first of all, that it runs really quickly, right? Here's now my function. So it still is like you're never going to quite get it until you get infinite numbers of terms. You're never going to quite get that discontinuity modeled correctly. But everywhere else, it's much better. You're seeing the oscillation dampen out. This hasn't changed at all. It's still really good. And then we can look at the surface plot. And the surface plot, that looks pretty good. You still see a little bit of oscillation in there. But in you know, as a whole, I think it's a pretty good solution technique for this. Some odds and ends to point out here. I want to just show you what it looks like, how you decide whether or not you have enough terms. So let's look at evaluating this. I'm going to set a breakpoint here and catch so we can look at the individual values. So I'm running this with 21. And I'm going to run in debug mode. And hopefully it'll catch. And so I want to look at the value T. This is our each individual temperature solution. So if we look at this value, T lam here, what we can see is the first eigenvalue, that lambda 1, accounts for 47.5 degrees of temperature. The second lambda accounts for 2.8. The third, minus 3.5. As you go further and further down, this is not showing up, but it's, yeah, it becomes e to the minus whatever. Like, so these are basically 0 as you get on here. This is at 0.5, 0.5 in the domain, right? But what happens if we model the same problem with the same number of coefficients and model it at right at that discontinuity? Now we're going to see something interesting. It's not converging, right? Every individual T lambda is accounting for about 0.2 degrees. And you'd have to basically go out to a very, very large number to get convergence, right? So this kind of thing, and looking at this, will tell you how many terms you're going to need, depending on where you are in the domain. OK, so we're out of time now. What I'll do is there's one more topic that I wanted to you guys to at least be aware of. It's called superposition. I'll just post the notes on that, and I won't test on it or anything, but it is worthwhile for you to look at, and we'll leave it there. OK, thanks, everyone.